Okay, so now I just want to say that we want to prove that it is independent of the choice of purification. Um, for one choice, then it holds for all choice. It means like you have any purification, you can try to rewrite it then with another purification, like no matter the type of purification, because before we take our terminal basis, and so we just have in a way like it was head on tail kind, like if you had like for example square instead of having 1 over 2 on 1 over 2 changes, or ABBB2 is easy, but you have like another basis where you should look at, which should look more quantum, or plus and minus, like you do not choose just your own biases. That's classical. You have all those weird bases. You want to say that even those weird bases, like our 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 solution, like um, our final equation will still be true. Like we will still have um, that condition two, um, with with like yeah, we could say like this condition will still apply. Like this condition is literally equal to another condition, like with a terminal basis, and that's the principle, of I think of Schumann theorem. Like it's that it can apply on those weird quantum base. So yeah, you have like or primes or n's the epsilon um, or r primes or m um, equal form. We're just about proving this. This distance is strictly equal, no matter like the weird choice we can do for f for doing the integrament with this pi. So yeah, basically the fundamental principle to arrive to this is just to say we have like we just have that if you have a pure state um, that are different ones for each other, like you just can apply um, a unitary about it, and or an isometry as you want. So it will still be equal. And for n copies, literally is the same, but just you take XOR to n, so you just AI XOR u or XOR n of psi XOR n AR. And so basically, because we transform our pure state into um, mixed, like because we purify, we needed to use the form of the mixed state, and so just to adapt it, for because we'll do encoding and decoding and do the subtraction of the stuff by the theorem, we still need here like to have a density matrix, because like for the channel it will be a density matrix, and after we will want to factorize. So yeah, that's why because we said at the beginning like we just wanted pure state, and so now we go because it was better for mathematics. But here, like you can't do it because there is a channel, and so you just need at first take this density matrix, even if after we'll go to to stuff without get state. So that's why we write it like this, to have the formalism mixed state, because there is a channel after. And so to simplify after it will be 0. So we just have this, and so it is the same as before, like here, of C of A XOR U unitary or M dagger, and you have the same, because encoder and decoder just act on system A. They commit perfectly with the unitary, and yeah, so basically it works also for the decoding and encoding parts. Well, anyway, you can ignore what I said, just have this, and so just replay just exactly the same. And so if we after inject the term into the calculator, the trace, now if we wanted to prove, don't know if I destroyed it there. Well, so I just want to check about it. Just like AX or UR or N, and all can be factorized by like rho A X or M minus the coding of rho A um, or M. Multiplied by like multiplied again by AI or UR or M here, and yeah, you have this, and so in a way here you can just use the fact that the the trace is like invariant by unitary transformation. U x dagger is just equal to x dagger is just equal to x, and um, and so because of this, it just means that we have rho AR 0n minus d 0 rho AR 0n, um, and yeah. And so we just prove like because AI XOR UR XOR N is just a unitary global operator, it can be directly destroyed, and so we just proved like what we wanted to prove, that the two trace distance are equal no matter the word choice we made for our system R. So yeah, that's cool. It just proves so no matter it just proves that so no matter what choice of purification you do, what choice of basis in a way or on some weird basis, we can still like no matter um, have the implication condition that will still be true, um, because that's the same condition at the end between both.